Hello, you fantastic physics students. Let's talk about working with vector formulas. First, big picture idea. We have all the skills we need for this already. We're just sticking two parts together. We know how to use our um, big five equations when we've got uniformly accelerated motion. So anytime we're working with acceleration, we know we're going to use these formulas. Previously, we've only done it with one-dimensional type problems, up and down, left and right, forward and back, and that's it. We're not mixing different kinds of directions. We're going to move into two dimensions now, and in order to do that, we need to add in our knowledge of vector addition. So we're going to kind of put these two ideas together. Their big strategy here when we're working with the problem is we're going to start it just like when we're working with these vector formulas. We're going to list our knowns and want to knows. We're going to pick the formula we're going to use. We're going to sub into the formula and we're going to work as far as we can until we hit a point where we're adding or subtracting some vectors. Then we got to stop, do that vector addition, and then we're going to go back and finish everything off. Okay, so it's kind of like we're sticking our vector addition skills in the middle of this type of stuff. Okay, so I'm going to take you through some examples, and then I'm going to have you try a good, meaty, challenging problem together in collaborative teams. So this one it feels like a normal kinematics problem. A car initially moving at 18 meters per second south executes a gradual turn in 8 seconds in order to reach a final velocity of 22 meters per second east. Calculate it to start off its displacement. Okay, so we're used to problems like this, but we're used to them being like south and south or south and north, not south and east. So we're going to have to add vectors in order to be able to conquer this problem. But let's start with the stuff that we already know. Let's start with listing our knowns and want to knows. We know our initial velocity is going to be 18. And I'm not going to put units in here just in order to save myself some space. So we're going to say it's 18 south. And we're going to say our time, we know that's listed, that's 8 seconds. We know our final velocity, that's one that we're given as well, that's going to be 22, but our direction is to the east. And the one we want to know is our change in displacement. What is our displacement? We're going to put a question mark next to that because we do not know the answer. Okay, let's pick a formula and we're going to work with that formula. Which one should we pick? I noticed that acceleration is not listed anywhere in here. So if we go back to the previous page, looks like our first formula is the one that doesn't include acceleration. So we're going to choose equation 1 to work on this. So let's write out equation 1. We're going to say our change in displacement is equal to, open the bracket, our final velocity plus our initial velocity divided by 2, and then we're multiplying that by our time, right? That's our equation. We're used to doing this. Now let's sub into our equation all the stuff we know. Our change in displacement is equal to, what's our final velocity? Well, it's 22, but in this case, we can't ignore the directions, right? Because we can't say south is positive and east is negative because they're perpendicular to one another. That's why this gets tricky. Okay, and we're going to add our 18 to the south, which is our initial velocity. And then we've got all of that divided by 2. And then our time is 8. So we're going to multiply all that by 8. You can see where we run into our problem, right? We're trying to add an eastern and a southern vector. We know how to do that, but it's stuck in the middle of a formula. So let's work out the math a little bit first. I noticed both of these numbers are divided by 2, and they're also multiplied by 8. So dividing by 2 and multiplying by 8, that's the same as multiplying by 4. I could have done it by dividing by 2 and then multiplying by 8, but that's an extra step I don't need. So just multiplying by 4, I end up with 88 to the east. And then I've got 72 to the south. Okay, now this is a pretty simple vector addition, right? We've got two vectors. They're right angles to one another. We can just draw a picture of that. So let's do that. Let's extend our page a little bit and draw ourselves a nice little picture. I'll go and grab some vectors. And I'm going to say, okay, I've got 88 to the east, looks kind of like that. And then I got 72 to the south, looks kind of like that. And east and south, and then I'm going to put on my resultant vector. It's going to come across like that. Let's do a little labeling here. I'll say this is 88, and I'll say this is 72, and I'm going to call this angle theta. I'm going to need to know that. And this is my displacement, right? When we add the two vectors together, that's what the formula says here, add the two vectors together, we get our displacement. So we got to figure this out. Well, this is a nice right angle triangle, right? Because we're dealing with east and south. So we know how to do that. Let's change colors to green, and we're going to go over here, and we're going to say, okay, right angle triangle is nice and easy. We're going to say our hypotenuse squared is equal to our other two sides squared. And then we'll square those numbers, take the square root of both sides, and that's going to give us our answer. Our displacement is going to be 113.7. Okay, awesome. Now let's do our angle. So we're going to say theta. This is going to be a tangent ratio, right? Because it's opposite and adjacent are the sides. So we'll say the tan inverse is opposite, that's 72, or our adjacent is 88. And so that means our angle is going to be 14.03624. I'll do lots of digits. I noticed I didn't do lots of digits up here. I could have done a bunch more, but we're like done this question now, right? So I'll just leave that alone for now. Now let's go back to red for our final answer. We say, what's our displacement? We're going to round this off to two significant digits. So 113.7 and change rounded off to 2 sig figs is 110. And units are meters. And our direction is going to be, looks like we're going east and then pointing to the south. So we're going to say east 14 degrees when we round it up to 2 figs to the south. There is our final answer. Let's throw a nice little box around that. Ta-da! Okay, that one's done. We figured it out. We used a vector formula, but we had some adding vectors that were perpendicular to one another in the middle, so we had to stop before we could finish with our formula and add the vectors using a diagram, Pythagorean theorem, and tan ratio. Okay, what if we want to find the average acceleration in this situation? Let's try that right now. That's part B. We're going to start off by writing our knowns and our want to knows. So initial velocity is 18, and it's to the south. Our time is 8 seconds. Our final velocity is 22 to the east. Maybe we don't need to rewrite this because we just wrote it above, but I think it's good to take stock because we've got a different want to know now. Okay, so given that we have these, I notice displacement isn't included here. Let's go back to our first page. Oh, when displacement isn't included, we're looking at this formula right here, equation 2. So let's use equation 2 for this. Here we go. We'll swap colors and we'll put in equation 2. Equation 2 is our final velocity equals initial velocity plus acceleration times time. We kind of want to isolate the acceleration, right? So before I plug some numbers in and make this a little messier, why don't I just get a by itself? So if to get a by itself, I'm going to subtract initial velocity from both sides. That's going to move it over there and make it negative. And then I'm going to divide both sides by t. So what we end up with is when we rearrange it is we've got our acceleration is going to be final velocity minus initial velocity divided by our time. I can see here that I've got my final and initial velocity subtracting one another, subtraction of vectors. Okay, we're going to need to figure that out. Let's sub into and see what we got here. Our final velocity is 22 to the east. Again, we're going to keep our directions in there because we need to know that because these are vectors that are not going the same direction, right? They're not in the same one-dimensional plane. And then we're going to subtract, because we are subtracting initial velocity, 18 to the south. Okay, we're also dividing all of that by the time, which is 8. Let's divide both of those numbers by 8. 22 divided by 8 is 2.75, and that's still to the east. And 18 divided by 8 is 2.25, still to the south. Okay, so I've got an eastern vector and a southern vector, and I'm subtracting them. I remember something about this. When I want to add vectors together, the negative of a vector means I changed its direction. So that's what I'm going to do here. I'm going to say that I need to add the opposite. That's a nice little note to myself to remind myself to add the opposite. Okay, let's get a little more room here, and we'll say we'll add the opposite. So that means I've got 2.75 to the east. And to change the subtraction into an addition, which is how we want to do it, we'll change it to an addition. And it's still 2.25, but instead of the south, now we're going north. I change the direction, and I change the sign. Okay, so I've got an east and a north. I can do that, an east and a north, no problem. Let's draw what this looks like. Okay, so let's get some vectors. And I got one going to the east. That's 2.75, looks kind of like that. And then I got one going to the north. It's 2.25, looks kind of like that. My resultant vector is going to look like that. And I can put my theta right here. I'll need to know that angle. Let's label the 2.75 was going east and the 2.25 was going north. And I've got my resultant vector here. What is my resultant vector again? Oh yeah, it's an acceleration. So actually, these two values, the 2.75 and the 2.25, those are actually accelerations. We got that because we had a velocity on top and we divided it by time. So we had meters per second divided by seconds. That's meters per second squared. So these are actually acceleration values. Okay, let's do the old dance we've done before, nice and easy. We're going to use Pythagorean theorem. We're going to use our tan ratio. We're really used to this at this point. Let's switch to green so we can see what we're doing. So we're going to say A is going to be equal to the square root of 2.75 squared plus 2.25 squared. What's that work out to? That's 3.55317. Great. Okay, let's do our tan ratio. So we'll say theta is tangent inverse. Tangent is opposite over adjacent. So we're going to say 2.25 divided by our adjacent, which is 2.75. When we work that out, we end up with an angle of 39.28941. Okay, so now we can write our final answer, right? Let's do that in red. We're going to say, okay, our acceleration, rounded to 2 significant digits for this one. It's going to be 3.6 meters per second squared. What's our direction? I can see that I'm going east and then turned up towards the north. So I'm going to go east 39 degrees, also rounded off to 2 sig figs, north. And you know what I like to do. Let's show the final answer. Let's put a box around it. Okay, nice. That box is not ideal. Could probably make that a little bigger. There we go. That's much nicer. What can I say? I'm picky. All right, let's move on to our second question. We've done 1A and B. Let's try jumping in on the next one. Okay, this one's a little more complicated. We're going to need to use vector components for this one. So I'm going to take you through, I'm going to list the steps we're going to follow, and I think you'll find that helpful to follow the steps. A speedboat initially moving at 20 meters per second west undergoes a displacement of 110 meters north 40 degrees west in 10 seconds. What's the boat's acceleration? Okay, we need to find the acceleration. Let's start the way we did before by listing our knowns and need to knows. Okay, I'm not even going to call that a step because we're just starting everything like that. Initial velocity is 20 to the west. Our displacement is 110 north 40 degrees to the west. Our time, 10 seconds. Our acceleration, we want to know it, but we don't know it. Let's think about what formula we're going to use. What are we missing here? We're missing final velocity. Let's go back to the beginning. Hey, right there, final velocity. So this is the equation we want to use. Ew, yikes, that's one of our more complicated looking ones. We're going to be okay. Let's use that formula. Let's just put it in here. We're going to say, okay, change in displacement is initial velocity times the time plus 1/2 times the acceleration times the time squared. That's our formula. Let's plug in a displacement. Okay, this is going to be a little long here. I'm going to say 110, but I got to keep the directions in here. North 40 degrees to the west. And you know what? Let's squeeze in, I should have mentioned this before. Let's call this step 1. And we're going to say sub into formula. Sub into formula. And let's put a nice little line under that. Okay, so we're subbing into our formula. Our initial velocity is 20 to the west. And we're multiplying that by the time. So the time is 10. So let's write it like that. And then we've got our 1/2, and we've got our acceleration. We don't know our acceleration, so we're just going to leave that as an A. And then we got our time squared. Our time squared is 10 squared, which we know is 100. Okay, let's simplify this a little bit. 1 on the left, not much we can do with. North 40 degrees to the west. But the stuff on the right, I can go 20 times 10 is 200, but it's still to the west. And then we've got 1/2 times A times 10 squared. 10 squared is 100. Divided by 2 is 50. So 50 times the acceleration. Okay, I want that acceleration. I got to get it by itself. So I'm going to subtract 200 west from both sides to move that one over. And then I'm going to divide both sides by 50. So I've got A by itself. So it's going to end up looking like this. We've got 110 north 40 degrees to the west minus 200 west, and all of that is divided by 50. So I just rearranged my equation there. Okay, we're getting there. Let's divide both of these by 50 because they're both being divided by 50. Let's see what we get. So we divide our first one by 50. 110 divided by 50 is 2.2. Direction's the same, north 40 degrees to the west. And now 200 divided by 50, that's going to be 4 to the west. Okay, good, except we're subtracting vectors, right? Okay, how do we deal with that? Ooh, let's add the opposite. We can do that. Let's add the opposite. Now, this is easy because it's west, right? If it was a more complicated direction, I'd recommend actually drawing it to make sure that you're pointing the opposite direction vector correctly. It's easy to make a mistake if it's at a weird angle. But west is easy. We just got to change that to east, right? No problem. So we'll say, okay, this is equivalent to 2.2 north 40 degrees to the west plus 4 to the east. I changed the sign and I changed the direction of the vector. Now we're just adding two vectors. We are very good at that. Let's do that. Let's add these two vectors, no problem. Okay, let's first, let's go to step 2. We're going to say draw a picture. We'll change it to green. Hey, green. There we go. Step 2, draw a sketch. Doesn't have to be perfect, but we want to have something that looks like kind of so we can picture this a little bit, hey, and have an idea about what we're actually looking at. Let's get some vectors in here. So my first one is north 40 degrees west. So that's going to go kind of like, I don't know, kind of like that. It's north, but it's 40 degrees to the west, kind of like that, right? And if I want to put in some dotted lines here, I can like draw some dotted lines in like that in order to make it a little easier to see. Oh, I don't want the arrowhead on there. Let's get rid of that. Let's try it again. I'll draw a little. There we go. That's what I want. Okay. So there's my first one. And I can actually label this one, and I think I will. It says north 40 degrees to the west. So that's like, that's 40 is in here. But I like the one next to the x-axis, so let's put that one in. That's a 50 right there. Now we need to draw our other vector. This one is just going east. So it's kind of like that. It's east. Let's label those. This one was 2.2 magnitude, and this one was 4 magnitude. Our resultant vector is going to look like this, right? Woohoo, there it goes. Hey, okay. But this is like looking pretty weird and ugly. I don't know how to add that. Let's just use vector components, right? Vector components. That's what we want. Let's use vector components. Okay, so we drew a sketch. Let's do step 3, calculate components. Let's do this in purple. We'll do it down here. We'll say step 3. Step 3. Calculate the components. Awesome. Now we know we like to use a table for this, right? So let's make ourselves a little table. We're going to say we got a vector, and we got an x component, and we got a y component, and we're going to need to figure those out. So like that and like that. Nice. First vector is easy. It's 4 to the east. What's my x component? It's to the east, so it's positive 4. What's my y component? Nothing. It doesn't go up or down at all. It's directly to the east, so my y component is 0. That's easy. I'm done. Let's do my second vector. That one's going to be 2.2 north, 40 degrees to the west. Now, if I look at my picture, I actually want to use this angle here that is next to the x-axis, right? Because I could use the 40, that's fine, but I want to use the one next to the x-axis because I'm more familiar with that. That means for the x component, I'm going to use cos every time. So I'll go 2.2 cos 50 degrees. That's going to give me my x component, but I want to recognize it's going west, so that's got to be negative. And then I got to do a little bit of math, right? I got to work that out. So that's negative 1.41413. Cool. Let's do my other one. It's going up, so it's going to be a positive number. So 2.2 sine 50 degrees. Calculate that out. 1.68530. Okay, did it. Let's add them up. Let's do our sum. We've got positive 4 and negative 1.4 and change. That's going to be a sum of 2.58587. Let's add this one up over here. 0 plus 1.6 and change. Oh, that's easy. 1.68530. Okay, so I got my vector components. We're close to done. It's a big, I know, there's a lot here. Hang on, we're almost there. Now we're at the easy part. What do? We got our x components. We got our y components. Let's draw a right triangle. Pythagorean theorem to calculate the magnitude. Tan ratio to calculate the angle. We've done this a million times before. And that's actually going to give us that same red vector. So let's draw it. Let's do our x component is going to be 2.5 and change in the positive x direction. The y component's also positive. It's 1.6 and change. We're going to put that right there. And our resultant vector is going to be just like that. Look, it's just like the other one. Because it is. It's the same vector. Okay, we're going to need to know theta. We're going to need to know this one. Again, this is an acceleration, right? Because that's what we're finding is an acceleration. Our components that we calculated from our table, we'll put them on here. Now we just got to do the old dance we're used to where we do the Pythagorean theorem and we do the angle. Let's do that nice and fast because we're talented at that now. The acceleration is the square root of these two numbers squared. What's that all work out to? That works out to 3.08658. I got lots of decimal places there. That's more than I need. Let's do my angle. Theta is the tan inverse. Tan is opposite, adjacent. Let's figure out what that angle is. That angle is going to work out to 33 and change. Okay, let's write our final one. We know we're finding an acceleration. We're rounding off to actually one significant digit in this case. So what do we round 3.08 off to? It rounds off to 3 meters per second squared. What's our angle? Round that off to 1 sig fig 2. East, 30 degrees, north. Hey, we did it. That was a little rough, but not too bad. We got there. Let's follow our steps. Let's just do a quick recap. We write down our knowns and want to knows. We pick out the formula we're going to use and we sub into the formula. We keep simplifying until we're left with just some simple vector addition. We draw a nice little sketch. Because this is some weird angles and not just right angles, we got to deal with vector components. We do our vector components. Once we're done the vector components, now it's going to be a nice right angle for us, which makes our lives easy. We draw our triangle using our vector components. We figure out the magnitude using Pythagorean theorem. We figure out the angle using tan ratio. Bob's your uncle. Well, at least Bob is my uncle. He really is. Okay, there we are. Now it's time for you to try and tackle one of these in a team. These are tricky. These are hard. There's no doubt about it. And they're long. But together, all of us are smarter than any of us. Time to jump in. Let's see how we do.